we did when we looked at the different types of plate margin, right? Do you remember? We looked at convergent plate margin, divergent plate margin, and transform boundaries. Do you remember?
Yes.
All right. We're going to be looking at the kind of magmatic activities that occur around those areas, okay? That form geologic processes like your landforms, your rocks, different kinds of rocks, or different kinds of geologic features or structures that are associated with those three, the two margin, both the convergent and the divergent. The transform fault, remember, we said there's really no rock forming there. Remember, we said it's just sliding of a plate against each other. And all it does is what? It generates earthquakes, right? We're going to look at that at the end of the class. But for now, let's look at the three type of volcanism that you're going to be looking at today. So associated volcanism refer to geologic processes and landforms that are created when magma erupts, okay? And this time around, we're looking at this magma formation associated with this convergent margin and divergent margin. So typically occurring at divergent convergent boundary and within stationary mantle like hotspots. We're going to see what hotspots is at the end of the class today. So we are looking at some convergence, which has to do with where tectonic plates collide. Remember, I told you that's the easiest explanation, right? And one pushed the other one beneath based on density. And if they are the same density, they crushed each other. That is, let's say, cross to cross. They pushed each other to form mantle, mountain belts like the Himalayas, the Alps, and the rest, okay? They form huge rocks. So while the divergence is the pull apart, where you have two plates being forcefully broken by pulling, you have stretching to pull it, remember. So this time around, we're going to add another type when we're looking at this volcanism. Volcanism, remember we say is the associated, the kind of magmatic eruption that is associated with these margins that we're going to be looking at. There is a type called hotspot that is not associated with either convergent or divergent. So it's standing on its own. We're going to see example. We have example even here in Nigeria. We're going to see how they form. So the hotspots are generally stationary magmatic plume that originate from the mantle. We are going to see how it formed. You know, I'll first of all introduce, then I start breaking it down one by one. So we are going to be looking at the first type, I think the magmatism that is associated with convergent margin. Then we go to those that are associated with divergent margin. Then we go to the hotspots. That is all we're doing today. Then we'll go to the next class. Sorry, my cursor is always late. So what is volcanism? You all know what volcanism is, right? You're a geology student. By now, you know what volcanism is. I just explained it in the last slide. When I said that volcanism is when magma generated from the mantle finds its way, that is, it pushes its way through the crust and erupts on the Earth's surface. That is magma coming in from depth, forcing its way all through the rock and pushing its way to the Earth's surface. So when it gets to the Earth's surface, you know, remember we say it's called lava. It's no longer called magma, right? When it gets to the Earth's surface. So that is volcanism. It is just the process of magma being generated from depth and pushing its way all the way to the Earth's surface. So we're going to be looking at different types of volcanism, how magma originates from the mantle and comes to the Earth's surface. So there are generally two causes of volcanism. The first one could be mechanical, but what we are looking at is mainly the ones that are associated with tectonics. That is the second one, that is location and ring of fire. because they are associated with tectonic plates. They formed where these tectonic plates are either diverging, opening up, pushing, allowing magma to come in, or converting, being pulled towards each other, and then it bends to a particular angle, and then because it moved towards the earth and the mantle, it starts remelting again and coming back to the earth's surface. So the volcanism is generally associated with tectonism, okay? Which is associated with tectonism, either divergent, convergent, or the last one, which is the hotspots we're going to be looking at. So the first type of volcanism we're going to be looking at is the volcanic arc. So what the volcanic arc is a long chain of volcanoes. You can see it here. You have, let me put the, just that if I put this pointer, it slows down my cursor. You can see it here. You have subduction taking place here. Let's start with this one. You have oceanic crust, you have subduction of oceanic crust, and it is richer in magnesium ion, it is heavier. It will go to the bottom of the lighter one, which is made up of feldspar and aluminum-rich minerals, okay? So this will subduct beneath this. But when this subduction is taking place, it continues going down. This one will be moving this way, this one will be moving this way, because they are jamming each other, and one is climbing the other one because of the weight. The heavier one went downward, the lighter one is more like floating on top of the heavier one. So it's the movement continues. Okay. So at a particular point, this one will start, it will move all the way down towards the mantle because it's being pushed down. The first, you can imagine this Earth's crust, continental crust pushing on top of it. So it's the weight is pushing this one downward. So it will get to a point that it will now get towards the mantle. And we know the mantle is very hot. So this rock will start remelting again. Do you understand? And when it starts remelting, remember, we said when rock melts, it loses some part of its density, it becomes buoyant, it's lighter. So it can float. You can see it forming small bubbles of all the aspects of. So is a just look, it is a stretch line formed is going beneath like this. Here, and the magma is forcing its way back up to the earth crust. It will form a chain of volcanoes. Chain is like line arranged. It is arranged. Look at one, look at two, look at three. They continue like that continuously. That's what they mean by chain of volcanoes. So the volcanic arc is a curved, right? Long chain is curved. Long chain of volcano formed above subduction zone. This is our subduction zone, okay? It formed above it. This subduction zone. So you can see the melting is taking place here. And because it is melting, the magma is pushing itself all the way up. And then it is forming new rocks, okay? But this time around, they form like a volcanic arc. You see them coming out like a volcano. So they form due to compressional forces that is melting these subduction plates. You have weight of this one, which is compressional force. You have heat also working on it from here. So definitely it will start melting. And the magma is what rises to form all this volcanic arc that you're going to see around. Do you understand? Hello? All right, this is the breakdown.
Yes, ma'am.
All right, the first thing you have is a heavy tectonic plate slide beneath another one. You have melting under high heat and pressure. Here, you have this magma forming, pushing itself up to the Earth's surface, and you have it erupting to form volcanoes. But this time around, it forms a chain of volcano continuously. Anywhere this subduction plate extend up to, you have this volcano forming at the top of it. So that is what a volcanic arc is. So another type of volcanic structure, sorry, that is associated with subduction plate is what is called the back arc basin. So this is a type of basin that forms. Basin is just like a depression or opening that allows either water or sedimentation to fill it in, okay? You have like a basin, just like what you know as basin. But this time around, it forms on the ground where you have a kind of opening. And then what generally happens is, remember there is subduction here, right? This is going down. It is melting. It is coming up to form volcanic arc here. This is a volcanic arc. But behind the volcanic arc, another activity is taking place, which is called the back arc spreading or back arc basin. Because this one is being pushed onto the subducting plate, the force of this one moving away from this other plate creates a kind of thinning of the crust. Okay? And you also know that this magma that is coming up will also affect this part. So there's a kind of thinning that is taking place here, whereby it's most times magma also find its way here, end up creating more like a ridge like a spreading ridge. But in some cases, like in the Japan area, it didn't create any ridge, but there is a spreading where you have this plate struggle and being pulled away because of the force at which this one is being pulled on top of this one. So there is a kind of Marconjo, let me finish explaining, okay? I'll allow you to talk. They generally form as submarine features. That is, they form under the water, okay? So what, like I was explaining, they are due to extensional forces. The force of this one being pushed on top of this subducting plate and this one lagging behind. Then you have the rollback of the effects of this one. So that is what causes this kind of stretching that takes place here. This heavy subducting plate, as it is sinking, it often pulls back. It has a force pulling back this one also down. Okay, it's called the rollback stretch. Remember, we look at it as one of the reasons for this subduction plate. So this rollback stretches the overriding plate, this overriding plate. And then it's caused the thinning of this crust. Remember, this is part of the crust. Look at it here, but you can see it is thinning. It's thinning up here. Okay, sorry, hold on. So on the board here, I said back arc formed behind a volcanic arc. Remember, we said this is a volcanic arc or the volcanic front. Remember, where there is subduction, melting. The first one we looked at, which now form this volcanic arc. So behind it is where you have your back arc basin. Do you understand? This is the volcanic arc. Behind the volcanic arc, you have your back arc basin. So those spreading centers are like mid-oceanic ridge, though the magma composition of back arc basin is generally more varied and contains higher water content than mid-oceanic ridge. It is similar to mid-oceanic ridge, like I said earlier, because it is kind of a pull apart basin. This one is being pulled apart from this, but there's slight difference in them, okay? So they are characterized by thin hot lithosphere. Thin in here, whereby this lithosphere thin, which opens up this arc basin, allowing parts of this hot asthenosphere to come in here. So they are characterized by some kind of mineralization, which we are going to be looking at later when we're looking at mineralization associated with these different volcanism. So this stretching, let me hit this further, because it is stretched, releases pressure. So you end up having some magma also pushing their way up here. So prominent examples are the Mariana Trough, in the Sea of Japan, like I said earlier, is formed by this kind of rifting, where you have a back arc basin forming behind the volcanic arc due to the subduction taking place. So because it forms a basin, you expect to have sedimentations occurring here, okay? So this is just example of how it forms. You have this subduction. We have our, okay, I think this diagram is not really doing it well. We're supposed to have our volcanic arc first before we have our back arc spreading centers around here. So you can see the separation, you can see the thinning of the crust here, forming the back arc. And because this force is pulling this one, the force at which this subducting and the overriding plate is moving away from this other plate, it makes this opening, which forms the back base, okay? So this generally occur at convergent plates where you have two plates bumping into each other. So generally, remember, their evolution is associated with stretching. The most important thing is this stretching that occur at the sites, which kind of melted some of the rock and made way for the arc and the basin to spread. Okay, somebody was asking a question, raise his hand. Sorry, you can ask your question before I continue. Somebody wrote, hello.
Excuse me, ma. I was one that raised my hand. It was because I was not hearing you, ma. But I logged out and I came back to the meeting. I can hear you now.
Oh, sorry. Sorry about that. Sorry about that. So for a back arc basin to form, there must be subduction. And this pulling of this force that is pulling this one away faster, okay? That is what causes a back arc basin. So they are generally found in areas where there's subduction, and they are generally associated with very old tectonic plates. That is not new subduction, does not generally form back at basin. It's restricted to mainly the old matured ones that are formed over millions of years. The spreading rate varies, okay, from each basin to each basin. The rate at which the faster, that is the rate at which this one is moving, sliding. Remember last time we looked at that some 2 centimeters, so different rates at which they move, the plate tectonics move, the plate are relative to each other. So each basin, the rate at which they also move, spread or open up is different from each other. So remember, some we said 2 centimeter last time, for some we said 6 centimeter, for some like the Mariana Trench move up to 15 centimeter per year. Okay, so it depends on the particular basin you're looking at. So another feature that is associated with plate tectonics is the oceanic trenches. I will explain, then I think the second diagram will show you what an oceanic trench is. Let me go back to it first. They are long, narrow depression that are formed that are associated with subduction zones also. Remember, this is our subducting plate. This is our volcanic arc, remember? Back arc basin is going to be at the back. Do you understand? We have volcanic arc here, so your back arc basin should be somewhere here. So this is what your trench looks like. They generally mark the exact location of the convergent plate boundaries. Okay? Do you understand what an oceanic trench look like now? Is this depression that is formed where the 2 plates collided? Do you understand? All right. So let's go back. Now that you understand it, this diagram will make sense. So you see oceanic trench here at the top. Where 2 plates meet, there is like a kind of like a formed. Remember, I said this is a continuous volcanic arc, a long range. Look at it continuously along all where the subduction is taking place. You're going to have the volcanic arc. Behind the volcanic arc, you're going to have your back arc basin. Same thing, continuous. Then here in the front, you're going to have your oceanic trench, which is the exact spot where these 2 plates collide. Because one is going beneath the other one at an angle, there is if you put your hand together, one above the other, and then you angle the lower one, you're going to see that there is a space, a kind of basin or depression formed at the top. So that is what is happening here. When this one is going down, this one is coming at the top. There's a kind of depression that is formed here. That is what is referred to as the oceanic trench. It is always the deepest part. So oceanic trench are narrow topographic loads that mark convergent boundary or subduction zone. Oceanic trenches average 50 to 100 kilometers wide and can be several thousand kilometers long. Oceanic trenches form as a result of bending of the subducting, the bending of this particular slab. Depth of oceanic trenches seems to be controlled by age of the oceanic lithosphere being subducted. Sediment filling oceanic trenches. You have sedimentation filling it here, just like it have at the back arc basin also. The deepest one is the Mariana Trench, which is the deepest point of the ocean at a depth of approximately 11,000 meters beneath the I think sorry, hold on. All right, yeah. It's beneath the sea level. So it's I wanted to know if it's from the surface or so it is beneath the sea level now, 11,000 meters beneath the sea level. That's about 36,000 feet below the sea level. That's to tell you how deep the Mariana Trench is. So oceanic trenches are steep V-shaped. If you look at it, they are V-shaped, formed by tectonic subduction, where one dense tectonic plate slide. We already understand that here. So another, we've already looked at it. You can see it is more like a V shape. Here, this is the trench. Do you understand what a trench is? Hello?
Yes, ma'am.
Do you understand, right?
Yes, ma'am.
So you understand volcanic arc, how it formed? You understand the back arc basin, which formed behind the volcanic arc? And now you understand the trench, which formed in front of the volcanic arc. You understand all that? All right. So I can go on, right? If you understand, do you have question? All right, let me go on. So the last one, we're looking at the hotspots today. Remember the last time, the ones we showed that the volcanism occur. They are associated with subduction, right? Like your volcanic arcs. But this time around, they are not associated with any plate tectonism. Do you understand? The ones we looked at, the volcanism we looked at are associated with tectonism, but this particular hotspot is not. It has nothing to do with convergent or divergent plate boundary. It occurs just on its own when a hot magma plume, for some reasons, finds its way all the way to the Earth's surface. That is what happened with the hotspots. So a hotspot is a place where magma rises from the Earth's mantle towards the Earth's surface. When magma erupts and flows on the, okay, you already know that. So what happened is that a blob of magma or just like kind of you know when your oil has sealed up and you put it on the fire, and the one from the bottom that first of all received the heat start finding its way all the way to the surface. Have you noticed that if you've melted oil before, right? Hello, maybe the ladies can tell us. Have you tried melting an oil that has congealed, or some people call it congealed, some people call it
Yes, ma'am.
concealed? All right, concealed or congealed. So what happened is that because the one that is closer to the heat is the first one that will heat up, you will see it. The face may still be solid, but you see one part will just push its way all the way up to the surface. You've noticed that before, right? So something like that is what is happening in the mantle. You have everywhere hot magma in a molten state. And for some reason, due to the heat, one part of the magma will just start pushing itself. You know, it's already buoyant because it's lighter than the crystallized continental crust or lithosphere. So it starts pushing its way all the way to the Earth's surface until it gets to the Earth's surface. So we're going to be seeing what causes that now. So this is like just like this. You have hot spots. This is deeper mantle, generally formed from deeper mantle. a magma will just start forming, coming all the way. Look at it. And then coming all the way to the Earth's surface. Why it forms range of volcanoes is because of the plate movement, which I'm going to explain. Remember that this one is coming from the mantle, right? Hello, let's talk. Let me know you understand me. Hello.
Yes, ma'am.
Yes, ma'am.
Please.
Yes, ma, we can hear you.
All right. So it means because it is coming from the mantle, it is not coming from the lithospheric plates. Because it is coming from the mantle, it means it is stationary, right? Remember, the mantle is not moving. Remember, right? The movement is due to asthenosphere beneath the lithosphere. Remember, right? Do you
Yes,
remember
ma'am.
all that?
Yes,
Good.
ma'am.
So it means this hotspot is stationary, it's not moving. Is the tectonic plates part of the lithosphere that is moving? Do you understand? So
Yes, ma'am.
if your magma hotspot is stationary and your lithospheric plate is moving in a particular direction, what will happen is that at a particular point, this magma will push itself to the surface. When the plates move away from there, it will move that one away. Another one, the next one, which formed on top of here, will burst out. Lithospheric plates or tectonic plates, sorry, will move away. Another one will burst out again. That is how it continues. Because the plate is moving, it now looks like it forms by chain based on the direction of the plate. This is our direction of the plate. Our hotspot is stationary. So this one was the first one that formed. The plate moved away. The second one is the next one that formed. The plate moved away. The third one formed. The plate moved away. Now we are on the fourth one. Do you understand the concept? Michael, ask your question. You have to shout. I don't hear well. You notice I always shout so that people can hear me. Not very, no. I can't hear you. Say the tectonic plate is formation of volcano, then I didn't hear you again. Does it not mean what? You have to talk louder, please. I'm using, hello? Maybe it's zero. I don't know because it's raining heavily here.